All right, so I think we're back. I'm just gonna kind of hang here for a second, wait for everyone to rejoin. So we'll get started in a few minutes. Just waiting for everyone to switch back over. Sorry about the technical difficulties, but it looks like we're all right. Get started in just a few minutes. All right, so let's continue on. Press on. Sorry about that. Technical difficulties. So we're going to keep going with this example here, and we had just started talking about it. So we'll just start over. So we're going to find the absolute max and absolute min value of this function f of x equal to x raised to the 1/3 power times 5 minus x. Defined on the closed interval -8 to 1. So we're going to use that extreme value theorem. So we're going to first check that our function is continuous. Then we're going to show that we see that it's defined on a closed interval, but because it's continuous and defined on a closed interval, we're guaranteed to have an absolute max and an absolute min. And that's what we're going to do. We're going to go through the closed interval method and show that this has an absolute max and an absolute min. All right, so what were the steps? First step, we wanted to check, is this function continuous? And this one is. It's a continuous product of a root function and a polynomial. So it's continuous on its domain. And odd roots, the cube root is defined over all real numbers. 5 minus x is defined over all real numbers. So this is defined everywhere, and it's continuous everywhere. All right, so that's the first step. We just want to make sure our function's continuous. And let me pause for just a second here and make sure, is everything sounding okay, looking okay? If someone could let me know in the chat, I just want to, hopefully, I don't know what happened there before. All right. So we got a continuous function on a root function and polynomial. So that's good. We can apply the closed interval method now. So what we want to do next is we want to figure out, we want to find our critical numbers. We want to find where f prime is equal to 0 or where f prime is undefined. So those are the two kind of things we're looking for. They give us an indication where we might have a local max or a local min. So we need the derivative. So that's what we're going to calculate here. We're going to calculate the derivative of this function, and we see that it's a product. We have that cube root times 5 minus x. It's a product. So we got to use the product rule. So let's implement the product rule. We write down 2 copies of our function. Put a plus sign there in the middle, and then apply the derivative to the first function, apply the second derivative there to the second function there. And that's our product rule. So we keep differentiating. So we just want to show that little step. It's easy with these more complicated derivatives. If you try to do everything in your head, you might make a little mistake here or there. So it doesn't hurt to show this step of applying the product rule. We're not done, though, getting the derivative, so we have to keep going. So we differentiate that x to the 1/3 power. We use just basic power rule. Then we have the 5 minus x outside. We're done with that. And then we keep going. And we have plus x to the 1/3, and then the derivative of 5 minus x is -1. All right, so we're done differentiating. So if that's all we had to do, we would be done getting the derivative for this function, but we need to do more work here. We need to figure out where the derivative is 0 and where the derivative is undefined. So we actually need to simplify that derivative in order to get it in a format that's easy to solve. So we see this term here with a negative exponent. So we're going to make that into a fraction. It's easier if we have negative exponents, try to get everything into a fraction. So let's see when we do that. We'll write this as, I'll put the 5 minus x for that first term in the numerator. And then we're going to have a 3 in the denominator and that x to the 2/3 power in the denominator. So we've made it into a fraction here. And then we also have that other term, the minus x to the 1/3. And that's looking okay. But we want to get a single fraction. That's going to make things a little bit easier. So to do that, we're going to get a common denominator. And so we're going to multiply this second term by 3x to the 2/3 over 3x to the 2/3 power. Just a fancy one to get our common denominator. And so when we do that, we're going to have 5 minus x from the first term. And then when we multiply those, the x to the 1/3 and the x to the 2/3, we add the exponents together. So 1/3 plus 2/3 gives us 1. So from that second fraction, we're going to end up with negative 3x. X to the power 1. And then this is all over the common denominator of 3x to the 2/3. All right. So there's our almost simplified fraction. We just do a little bit more. And we just clean up the numerator just a little bit. 5 minus 4x all over 3x to the 2/3 power. All right, so that's about as good as we can get it. And now we want to actually figure out where does the denominator, or where is the derivative 0, where is the derivative undefined, and why it's useful to get it into this form of numerator and denominator is because when we look for where f prime is equal to 0, when we have a fraction, that happens exactly where the numerator is equal to 0. And when we look for where f prime is undefined, and we have a fraction, well, that happens exactly where the denominator is equal to 0. Usually. We might have other things like square root functions or natural logs, but for just a fraction, we're looking for where the numerator is 0 and where the denominator is 0. So we take our numerator, which is 5 minus 4x, we set that equal to 0, and if we solve, we get x is equal to 5 over 4. So that's from the numerator. Then to figure out where f prime is undefined, we set the denominator term equal to 0, so 3x to the 2/3 power. We set that equal to 0. We go through the same thing, solve that for x, and that's x equal to 0. So, trying to simplify our derivative down into a single fraction will make things a bit easier here in terms of actually then solving for x. And so we just want to check these are the critical numbers of our function f. And they're in the domain of our function f. So we could plug 5 over 4 into the original function. Makes sense. We don't get any, division by 0 or negatives under square roots or anything like that. Same thing with x equals 0. We could go back to that original function, plug it in. We don't get anything undefined. So those are in the domain of our function, so they're critical numbers. All right, so that's the bulk of our work here, is calculating the derivative and then figuring out where it's equal to 0 and where it's undefined. Step 3 is then to evaluate our original function. So we're always going back now to our original function. We're going to plug in our critical numbers and we're going to plug in our endpoints of our interval. Those are the only possible places where we might have an absolute max or min. So we're going to take, let's start with our endpoints here. So we'll take 1 and plug it into the original function. We'll take -8, we'll plug that into the original function. And then we need to plug in our critical numbers, but we're not going to plug in all our critical numbers. We're only going to plug in the ones where our function is actually, or we're only going to plug the critical numbers that are actually inside the interval. So that other critical number, x equal to 5 over 4, we're not worried about it because it's not inside this interval, this closed interval here. It's outside of that interval, so we can't have a max there or a min because we're not even considering it. So we don't have to worry about using that critical number in our calculations here because it's not in our interval. So we're only worrying about the endpoints of our interval and then any of the critical numbers that happen inside that closed interval. So 0 is the only one. All right, so let's plug 1 in. We plug it into the original function. And in this case, we get 4. Let's plug -8 in. So we get -8 to the 1/3 power, 5 minus -8. And if we do that, -8 to the 1/3 power is -2. So if we do this, we get and 13, so -26. Okay, and plug 0 in. Plug the other critical number in, or plug the only critical number in that's inside our interval. So we plug 0 in, and we get 0. All right, so the last step then is just to go through and compare which one of those is our maximum value and which one is the smallest value. So that's the last step. We just compare. And what we see here is the largest value is 4. So that's our absolute max. The absolute max is equal to 4, and it occurs at x equals 1. And then we go through and we find our minimum, the smallest value, and we see that right here with the negative 26. It's the smallest value. So the absolute minimum value of our function is negative 26, and that happens to occur at the other endpoint. So it doesn't have to happen where it occurs at both endpoints, but in this example, the max happened at one endpoint, the min happened at another. And so there's our final result. So we just want to figure out where the derivative is 0, where it's undefined. Once we figure those critical numbers out, we throw out any of the critical numbers that are not inside our closed interval that we're considering. And then we just plug in the endpoints and any of the remaining critical numbers, and then we just compare the numerical values there and pick which one's the largest and which one's the smallest. All right, so that's kind of the gist here. So it's a very systematic way to go about this. Let's try one more. Let's look at the function e raised to the 1 over x with x between 1 and 10. So we have a closed interval there, so we know, well, hopefully if our function's continuous, we know we're guaranteed then to have an absolute max and min. Now this one we do have to be a little bit careful with. So our function is not always continuous. But our function here is continuous everywhere except at x equals 10. Or not 10, 0. 10's okay. Everywhere except x equals 0. Why? Well, because we have that 1 over x right up there in the denominator. And so there's like a little tiny fraction up there in our exponent, and when that denominator becomes 0, the result is undefined. So when we try to plug 0 in, we get e raised to the power 1 divided by 0. 1 divided by 0 is undefined, so our function is undefined there, so it's not continuous. But we're only looking at that closed interval from 1 to 10, so 0 really doesn't matter. So it's outside our interval, so it doesn't really matter in terms of finding an absolute max or an absolute min here. So our function is continuous on that closed interval, and we're dealing with a closed interval, so we're guaranteed to have an absolute max and an absolute min. So step 2, we want to find the critical numbers. Those are the only places where we could, inside that interval, where we could potentially have an absolute max or an absolute min. And then also possibly at the endpoints. So we need to figure out f prime. So let's go through and do our derivative. Now we have an exponential function with a more complicated exponent, so we have to use our chain rule. So we start by applying the general exponential rule or general chain or chain rule, and the way it works for functions like e raised to a complicated exponent is the exponential part stays the same, and then we multiply by the derivative of the terms in the exponent. And again, when you're doing these problems where you're going to be doing possibly multiple derivative rules, it's best to show your work. And that's what we're showing here. We don't try to do it all in one step. We're applying the chain rule here. So let's show that step of actually doing the derivative then of the inner function. All right, so let's continue on differentiating e to the 1 over x. We're done with that part. So the exponential part stays the same. And then derivative of 1 over x is negative 1 over x squared. I'm not showing all my work there. But what you would do is you would say, okay, let's rewrite 1 over x as x to the minus 1. Then apply the power rule. So bring down the negative 1, subtract 1 in the exponent, and then we go back to a fraction. So, you might be able to do 1 over x, derivative of 1 over x in your head, but if you don't see how to do it, rewrite it with a negative exponent. But for the purposes of actually figuring out where this derivative is 0 and where it's undefined, negative exponents, it's better to convert negative exponents to a fraction. So that's why I go back to a fraction. And let's just kind of consolidate this into one single fraction here. So I'll put that e to the x on top, or e to the 1 over x on top. So we'll have e to the 1 over x divided by x squared with a negative in front. All right, so that's our derivative. It's as a fraction. So we want to figure out where our derivative then is equal to 0. And we want to figure out where our derivative is undefined. And the nice thing when we have it in a fraction, where the derivative is equal to 0 happens exactly where the numerator is equal to 0. And our derivative is undefined when the denominator is equal to 0. So trying to get everything into this fraction form really kind of helps figure these potential critical numbers out. All right, so let's start. We'll take the numerator. We'll set that equal to 0. So e to the 1 over x, we'll set that equal to 0. And when we have just a single exponential function, e raised to something, it really doesn't matter what that something is. There's no way e raised to anything can be negative. So none. There's no way this derivative can be equal to 0. And that's because this exponential functions are never negative or never equal to 0. When it's just e raised to something, doesn't matter what that something is, exponential functions are never equal to 0. All right, so that's not too bad. What about the denominator? Let's set the denominator equal to 0. We get x squared equal to 0, and that actually does give us something. It gives us x equal to 0. All right, so that's a potential critical number, but as we said, it's really not, because our original function is not defined at x equals 0. So even though we found this, it doesn't really tell us any new information. So this is not actually a critical number. Because f is undefined. It's undefined there. It's not in the domain of f. So there's no critical numbers for this function. So when we're trying to figure out the absolute max and the absolute min on this closed interval, the only place that could happen is at the endpoints. So we just need to evaluate. So we're only plugging in the endpoints here. So we're going to plug in, we'll do 10 and we'll do 1. So when we plug 10 into this function, we get e raised to the 1 over 10, which is e to the 0.1. And when we plug 1 in, we get e raised to the 1 over 1 power, which is just e. And e is the larger value there. So we go through and we just compare the results, and there's only 2 results to compare. So the larger of those two values is the absolute max, and the smaller is the absolute min. So that's what we're seeing. Absolute max is equal to E, and that occurs at x equals 1. And then the absolute min is equal to e to the 0.1, and that occurs at x equals, at the other endpoint, x equals 10. So this example really illustrates the process is generally the same, but really the interesting thing here for this example is we got that result, x equal to 0, that satisfies, you know, some of the conditions for being a critical number. So our derivative is undefined there, but it's not technically a critical number because our function, the original function f, is undefined there. So we can't actually have a max or a min at that value x equals 0 because our original function is undefined. So even though it fits a lot of the description for what a critical number is, there's that one little piece that we have to be aware of, and that's where our function, it has to be defined there. All right. So we're going to use a lot of this in the upcoming sections. So a lot of these techniques and steps here are going to feel very similar. So we'll stop there with the closed interval method. So for finding absolute maxes and mins for a continuous function on a closed interval. What we're going to talk about next is the intervals of increase and decrease. So our next outcome is 03, and this is where we just find the intervals of increase and decrease for a function. And we'll start by kind of just reviewing here. For an interval from a to b, for an open interval, and we're primarily going to be talking about open intervals here, if f prime is positive, then f is increasing. So if f prime is greater than 0, if f prime is positive, what that means is our original function is increasing. And if f prime is negative, if f prime is less than 0, what f prime is telling us the slope of the tangent line. So if f prime is negative, it means the tangent lines are pointing down. So our function is decreasing. So if f prime is negative, our tangent lines are pointing down, and that means our function is decreasing. All right, so we're going to use this. So the strategy we're going to use to figure out the intervals of increase and decrease are, we want to find where the derivative is positive. We want to figure out where the derivative is negative. And so our steps here, step 1, we first need to calculate the derivative. Step 2, we need to figure out where the derivative is equal to 0 and where the derivative is undefined. Then we're going to create a sign chart for f prime, and then we'll figure out the sign of f prime on each of the resulting intervals. And so we see these gadgets again. We want to know where the derivative is equal to 0. We want to see where the derivative is undefined. And why we're so interested in the case of figuring out where f prime is positive and where f prime is negative, these are the places where f prime can switch signs. So it can go from positive to negative. So the only places where f prime can switch signs is either if it crosses the x-axis, so it's equal to 0, or if it jumps over the x-axis where it's undefined. So those are the only two possibilities here. So to figure out the sign of f prime, we will first need the derivative. Then we want to figure out where it's 0, where it's undefined. Those are the places where it can actually switch signs. And then we'll do our sign chart to figure out the sign of f prime in between. And so those places where f prime is 0 or undefined, we gave those a special name in the case of when the number is actually in the domain of f. So again, we called those the critical numbers. So for our purposes here, we're interested in both the places in the domain and not in the domain. And so when we do our sign chart, we're going to draw a number line, and then we'll put some dots on there for all the potential critical numbers. So we're going to use a filled in dot for an actual critical number. And what we mean by that is the derivative is equal to 0 there, the derivative is undefined there, and it's in the domain of f. And we'll use an open dot on our number line to indicate a non-critical number. So something that almost fits the description, but not quite. So not in the domain. So it'll be one of those places where f prime is 0, where f prime is undefined, but we'll use an open dot to indicate if it's not actually in the domain of our original function. So let's see an example of how to go through this. So let's start with the function f of x equal to 1/3 x cubed minus 2x squared plus 3x plus 1. And we want to find the intervals where this function's increasing and the intervals where it's decreasing. So let's see how this process is going to work. Step 1, we need our derivative. So that's what we have to do. We have to calculate our derivative. So this is a polynomial. So let's just go through term by term, differentiate everything. Differentiate the first term, we get x squared. Differentiate the second term, we get 4x. Differentiate the third term, we get 3. And then the derivative of 1 is 0. All right, so that's our derivative. Now we know we're going to be trying to figure out where that derivative is equal to 0, where it's undefined. So to simplify that process, we want to factor this. And it factors nicely. It factors into x minus 1 times x minus 1. So this is going to be a step. As soon as you get the derivative, you want to try to simplify it down. And the way we're going to simplify a lot of these is by just trying to factor it. All right. So now in step 2, we want to figure out where f prime is 0 and where f prime is undefined. So let's start with setting it equal to 0, and we'll try to solve for x. So we'll set our factored version equal to 0. And the nice thing about a factored version is then we can set each of the factors equal to 0. So that's why factoring is one of our nice solution techniques for solving for x, is because then we can just take each of those simpler individual factors and set those to 0. So we set x minus 1 equal to 0, we set x minus 3 equal to 0, and then those are easy to solve. So we get x equals 1 and x equals 3. All right, so those are values for x where f prime is equal to 0. Now let's look for places where maybe the derivative is undefined, but we actually don't see any for this function. The derivative here, what is our derivative? It's x squared minus 4x plus 3. There's no fractions, there's no square roots, there's no natural logs. That's always defined. So f prime always exists, so there's no contribution from that. All right, so the next step then is to actually go through our sign chart. So we're going to draw in a number line. We're going to plot those x values that we just found. So we found x equals 1, and we found x equals 3. And we just want to check, are those values in the domain of our original function, or are they not in the domain? And our original function is a polynomial. So, here's our original function. There's no division by 0. There's no square roots. There's no natural logs. So our function is always defined. So these are actually critical numbers. So both of these x values that we found are indeed critical numbers because they're in the domain of our function f. So we do want to keep track of that. We'll see why that's important a little later on. But for right now, we're just going to use those closed dots to indicate that those actually are in the domain of our function. And what they do is they split up the x-axis, in this case, into 3 intervals. So we have the interval from -infinity to 1. We have the interval from 1 to 3. And then we have the interval from 3 to infinity. And so on our sign chart, what we're going to do is we're going to look at each factor of our derivative. So we factored it. It was x minus 1 times x minus 3. So we're going to write down each of those factors and then see what that tells us about f prime, and then ultimately see what that tells us about f. Is it increasing or decreasing? And so what we're going to use, we're going to go through in step 4, we're going to actually fill out this sign chart. So we're going to figure out the sign of each of those factors on each of those intervals. And one way to do that is with test numbers. So that's step 4. We're going to fill in this sign chart, and we can use test numbers to help us do that. So for instance, for that first interval, -infinity to 1, we just want to pick a number that's somewhere in that interval. And what we can do is we can plug it into each of the factors and see if we get a positive or a negative result. So let's pick something in this first interval. It has to be less than 1. So pick anything less than 1. 0 is always good. So let's pick 0. And let's plug it into each of those factors. So when I plug 0 into that x minus 3 factor, I get a negative. I get -3. So it's negative there. When I plug 0 into that other factor, x minus 1, I get 0 minus 1, which is -1, so I get a negative. And so our original function, or original derivative there, was x minus 1 times x minus 3. It was the product of those two factors. So when we take a negative result, multiply it with another negative result, the result is positive. So f prime is positive on that entire first interval, and that means our function is increasing on that entire first interval. And that's it. We just play the game for every single interval. So now let's go to that middle interval, the interval from 1 to 3. We want to pick a number that's in between 1 and 3. So let's pick 2. Try to keep it as simple as you can. Now we plug 2 into each of those factors. So going into the first factor, we get 2 minus 3. We don't really worry about the number. We just want to know, is it positive or negative? So 2 minus 3 is negative. Then we go to the other factor, 2 minus 1, that's positive. And so when we take a negative number and we multiply it by a positive number, the result is negative. And that means our original function is decreasing on that interval from 1 to 3. One more interval, 3 to infinity. Let's pick a test number. So something bigger than 3. So maybe 4. Doesn't matter. Could pick 5 or 10. Whatever's easiest. Let's plug 4 into that first factor, the x minus 3. So we get 4 minus 3, which is a positive result. Then for the x minus 1, let's plug the test number into x minus 1. We get 4 minus 1, which is positive 3. We only really care about the sign, so it's positive. And when we have a positive number times a positive number, the result is positive. So if f prime is positive, then it is, our original function is increasing on that interval. And that's it. We just then formally write down our results. So we found that our function is increasing on the intervals minus infinity to 1, and we'll write it as comma separated. So so we'll write it as it's increasing on the interval from minus infinity to 1, and then on the interval from 3 to infinity, and we'll just put a comma in between to separate those two intervals. So it's increasing separately on those two intervals. And then finally, let's write down where it's decreasing. So our function is decreasing on that middle interval from 1 to 3. All right, and that's the game. So we're just going to play this game a bunch of times for more complicated functions. So let's try another one. Let's look at x to the 4 minus 4x cubed. And we're going to figure out the intervals of increase, decrease for this function. So step 1, we need our derivative. So let's calculate our derivative. And what do we get? We get 4x cubed minus 12x squared. And we know we're going to try to figure out where this is 0, where it's undefined. So might as well just do it right away. Let's try to simplify and factor as much as we can. So we can factor out a 4. Both of those terms have a 4. And both of those terms have 2 copies of x. So we can factor out an x squared. And so when we do that from the first term, we're left with an x. And when we do that from the second term, we're left with a 3. So this factors into 4x squared times x minus 3. All right, so now in step 2, we want to figure out where f prime is 0 and where f prime is undefined. Our function here is a polynomial, so the derivative is always defined. So we'll just get that one out of the way first. Our derivative is never undefined, so we're not going to get any x value there, so none. But our derivative might be equal to 0, so let's work on that one. So we take the factored version of our derivative, set that equal to 0. That gives us the equation 0 is equal to 4x squared times x minus 3. Because it's already factored, we can just set each of those individual factors equal to 0. So we get 4x squared equal to 0, x minus 3 equal to 0, and each of those is easy to solve. So we get x equal to 0 and x equal to 3. Now, we found those x values. Let's just check. Are they actually in the domain of our function? And they are. Our function is a polynomial. It's always defined. So both of these are critical numbers, and it's because they're in the domain of our function f. So when we do our sign chart, we're going to fill in the dots there. So there's a question about dividing by x minus 3. And it's better not to divide by a variable. And the reason is because as soon as you start dividing by variables, you might lose an x value. So just a little kind of aside here. So let's kind of keep track of these critical numbers that we found, x equal to 0 and x equal to 3. And if I were at this step here, if I had 0 is equal to 4x squared times x minus 3, it's very tempting to say, all right, let's divide by x minus 3 or divide by x squared. So what happens if we were to divide by x squared? We would get 0 is equal to 4 times x minus 3. And if we were to solve that equation, we would get only x equals 3. So as soon as you start dividing by an x term, you risk losing one of the critical numbers, losing one of the critical numbers there. So it's better to follow this approach where you get your function factored like we did, and then you set each of the individual factors equal to 0 and solve those equations. So you try to get it factored as much as you can. As soon as you start dividing by x or x minus 3, you risk throwing out potential critical numbers. So that's a good question. That's a very common thing that I see. So as soon as you start dividing by x, you have to worry because you might be getting rid of a potential solution. All right, so we got our derivative. We have where our derivative is 0, where it's undefined. Now we do our sign chart. And I'm going to need a little bit more room there. There we go. All right, so let's plot 0 and 3 on our number line here. So this is just the x-axis. And let's plot 0, and we'll plot 3. And then because those are critical numbers, they're in the domain of our function, we'll just indicate that by just filling in some dots there, just to remind us that those are actually critical numbers. That'll be important later on. Then we're interested in going a little bit further with this and figuring out local maxes and local mins. But for right now, those numbers split up our number line into 3 intervals. The interval from minus infinity to 0, the interval from 0 to 3, and then the interval from 3 to infinity. So we've split things up. And what we're going to do is we're going to look at each factor of our derivative. So we're going to go back to the factored version of our derivative and just take each of those individual factors, so the 4x squared and the x minus 3, and we'll look at the sign of each of those individual factors and see what that tells us about f prime, and then ultimately what that tells us about our function f. And so to help us kind of fill in this sign chart, you might want to use test numbers. And then just pick a number from each of the intervals, plug it into each of the factors, and see if you get a positive or a negative result. So let's start with that first interval on the left. We want something less than 0, so -1 works. And that first factor, the 4x squared, 4 is positive, x squared is always positive. So anything with an even power like that is always going to be positive. So we don't even need to really use a test number there. We can just say this 4x squared is always going to be positive. So we'll just go right down the row. Everything's positive. All right, what about that x minus 3? So let's plug the test number into x minus 3. We get -1 minus 3. It's -4. So it's negative. We don't really care about the number. We care about the sign, so negative. And so when we take a positive number, multiply it with a negative number, the result is negative. And that tells us the original function then is decreasing on that interval. All right, let's go to the middle interval. Pick a number between 0 and 3. 1 is always good. Plug that into x minus 3. We get 1 minus 3, and that's negative 2. So we don't really care about the number. We just care about the sign. It was negative 2. It's negative. So when we take a positive number, multiply with a negative, the result is negative. And so that tells us the original function is decreasing on that middle interval. And then finally, we go to that last interval. Pick a test number. So we want something bigger than 3. Keep it easy, maybe 4. 4 is not too bad. And plug that into that remaining factor. We get 4 minus 3, which is positive 1. So we get a positive. So we're taking a positive number, multiplying it by a positive number. The result is positive, and that tells us the original function then has to be increasing on that interval. So let's just write down our results. We've shown that our function is increasing on the interval from 3 to infinity, and it's decreasing on the interval from minus infinity to 0 and the interval from 0 to 3. And that's fine to leave it like that. We could actually go a little bit further for that decreasing and combine those two intervals together because they're right next to each other and f is continuous at x equals 0. So not necessary, but it doesn't hurt to just mention this. We could say the interval from minus infinity to 3. And we can't always do that. The intervals have to be next to each other, and the function has to be continuous at x equals 0. So because those intervals are right next to each other and the function is continuous at 0, we can say that just overall f is decreasing on that interval from minus infinity to 3. All right. Let's try another example where things get a little bit more involved. So the function 2x squared over x squared minus 1, we're going to go through and figure out where this function's increasing, decreasing. And let's start by going through our steps. We need f prime. So here f prime is going to be a little bit of work. We have a fraction here, we have a quotient, so we need to use the quotient rule. So let's start by just implementing the quotient rule. So we'll show our work. So we write down our quotient as a product, top times bottom, top times bottom. Put a minus sign in between, and then in the first copy we differentiate the first function, second copy we differentiate the second function, and then it's all over the original denominator squared. So don't try to do too much in your head, especially for these problems where we actually need to have the correct derivative in order to get the correct answer later on. So just a little mistake in the derivative here is going to kind of stick all the way through. All right, so let's keep differentiating. So derivative of 2x squared is 4x. Then we have x squared minus 1 minus 2x squared. And then the derivative of x squared minus 1 is 2x. And then we don't do anything to our denominator. We just leave that alone. And then we want to try to simplify as much as we can. So, if we were just getting the derivative, that would be fine. But we're going to be doing some work with this. So we need to simplify it down as much as possible. So really, most of the work happens in the numerator. So let's multiply the numerator out, all the terms in the numerator. So we'll distribute the 4x, and then we'll just multiply these two terms together. So we get 4x cubed minus 4x, and then we have minus 4x cubed for the second part there. All over x squared minus 1 squared. We don't really do anything with the denominator. 4x cubed minus 4x cubed, those terms cancel, and we're left with just a negative 4x over x squared minus 1 squared. So we had to use quotient rule. We had to simplify our derivative down, and that's about as good as we can get it. So now the next step is to figure out where this derivative is 0 and then where the derivative is undefined. And the nice thing about having it set up as a fraction like this is we can just look at where the numerator is 0, and that'll tell us where the derivative is 0. And to figure out where the derivative is undefined, well, we just have to look at where the denominator is 0. So once you get it simplified into a fraction, it's not too bad to go on and figure out where the derivative is 0 and where the derivative is undefined. So let's start with the numerator. We'll take the numerator term, negative 4x, we'll set that equal to 0, and that's not too bad. That gives us x equal to 0. Now let's go through and set the denominator term, x squared minus 1 squared. We'll set that equal to 0, and let's try to solve that. So we could apply the square root to both sides, and it doesn't really matter here, but whenever we apply the square root in our solution process, we need to put a plus minus in front. So this technically should be plus minus square root 0, but it doesn't matter because it's going to be 0. So that would give us x squared minus 1 is equal to 0. And we'll do it again. Let's solve for the x squared, and then we'll apply the square root. So x squared equal to 1. Let's apply the square root. Another way to go about that would be to just factor. So you could factor x squared minus 1. But let's use this other approach just for the practice. Let's apply the square root to both sides. And whenever we apply the square root, so we're going through the solution process, we're applying the square root, that's where we put the plus minus in front. If the square root's already there, then there is no plus minus. But whenever we actually write in the square root as part of our steps to solve for x, that's where we put the plus minus. So it's a very common mistake is to forget about that plus minus. So it's good to mention it. So we actually get two x values here. We get x equal to positive 1 and x equal to negative 1. And that's it. We figured out where our derivative is 0, where our derivative is undefined. Now let's just mention here, x equals 0 is a critical number because it's in the domain of our original function f. We can plug 0 in back into the original function and we get something that makes sense. But for these other numbers, 1 and negative 1, these are not critical numbers. They're close. They do meet some of the requirements, but they're not in the domain of that original function. If you were to plug 1 in, you'd get division by 0. That's undefined. So these are not in the domain. They're still important, but we do want to keep track of whether they're in the domain or not. All right, so let's use this result to actually do our sign chart and see how that looks. All right, so we found previously on the last page there, we figured out the derivative. We figured out that x equals 0 was a critical number. and we figured out that x equals 1 and x equals number 1, or negative 1, were close, but not quite. They weren't in the domain. So we'll just call those non-critical numbers. Almost, but not quite. They're not in the domain of the original function. All right, so let's do our sign chart. Get our sign chart set up. We're going to draw our x-axis. Give myself a little more room there. And we're going to plot those numbers that we found. So -1, 0, +1. And x equals 0 was a good critical number, so we'll fill that in with a closed dot. And we're just keeping track of things that are in the domain, because that's where ultimately, as we'll see later on, where we might have a max or a min. Those non-critical numbers, they almost meet the requirements, but not quite. Our function's not defined there. So we're going to use just open dots, just as a visual reminder. So those split up our number line. Into, in this case, 4 intervals. So we're going to have 4 intervals to check. And what we're going to do is we're going to look at each of the factors of our function, of our derivative. So our derivative has 2 factors. It has this negative 4x, and then it has this term in the denominator. So let's put down those 2 factors, and we'll see what they tell us about f prime, and then ultimately what they ultimately tell us about our original function f. So let's start with the easy one. This term has a squared on the outer, so whenever we square anything, it's always going to be positive, or maybe 0. But if we're squaring something that's not 0, it's ultimately going to be positive. So that's an easy one to check. We can just go right across. Always positive. Now for that negative 4x, maybe we use test numbers there. So if you need to, use test numbers. If you can just kind of figure out where it's positive, where it's negative, that's fine. But sometimes helps to just plug something in and see what you get. So for this first interval, we want something less than -1. -2 would work. So let's plug that test number into the factor -4x. When we do that, we get -4 times -2, which is +8, so positive. For the next interval, maybe we use something like -1/2. Plug that into the -4x factor. We get -4 times -2. It's positive. For the next interval, something between 0 and 1, maybe 1/2. Plug 1/2 into the -4x factor. We get a negative. And then maybe our test number for something bigger than 1, we'll use +2. So when we plug 2 into that -4x term, we get -4 times +2, we get -8. We don't really care about the number, we just care about the sign. It's negative. So when we take a positive number, divide it by a positive number, the result is positive. Same thing for the next interval. When we take a positive number, divide it by a positive, the result is positive. Negative divided by positive is negative, and negative divided by positive is negative. So we've figured out the places on our interval here where f prime is positive and where f prime is negative. And so what that tells us about our original function is on that first interval, our original function's increasing. It's increasing, then it switches to decreasing, and then it's decreasing. So let's just kind of write the results here. F is increasing on the intervals -∞ to -1 and from -1 to 0. And f is decreasing on the interval from 0 to 1 and the interval from 1 to infinity. And we can't combine those intervals like we did in the last example. So if you wanted to just kind of consolidate those, each of those into one interval, you can't actually do it because our function is undefined at x equals -1 and x equals +1. So it's tempting to just say, all right, let's just get rid of the middle number there, the -1 and the +1, and just look at the overall intervals, but we can't do that here. And that's because our f is undefined at x equals +1 and x equals -1. So we can't actually combine those. All right, so we'll stop there for today. We'll look at a couple other examples next week of figuring out intervals of increase, decrease. And then we'll look at a very similar process, almost the exact same process for finding intervals of concavity. But there it'll be figuring out where f double prime is positive, negative. So the process will feel very similar. We're just going to be dealing with a different derivative. All right, so let's stop there. And just one last reminder, the fall homework extravaganza, all the old homework assignments have been reopened. So, keep that in mind. They're due now on Monday, so you have a few days to kind of go through and finish any of the assignments you didn't finish before. And for anyone in Thursday's recitations, you'll have your exam today, so we'll see you in a little bit. So good luck as you finish up studying and as you get prepared for the exam. All right, so we'll stop there. Have a good weekend, and then we'll see everyone next week, Tuesday, for lecture. Bye-bye.